questions from the Nelson Physics 12 textbook, page 201, number 6. It involves kinetic energy, gravitational potential energy, conservation of energy with friction. You're given a skier, 55 kilograms, sliding down a slope with friction, the initial and the final speeds provided, and you are to determine the angle of the slope from the law of conservation of energy. As always, we're going to start off with a really good diagram. So let's draw this slope. Ultimately, this angle phi is what we're going to solve for. Our important positions are at the top and the bottom of the slope, so we'll call those A and B. Down here at B, it's our lowest position, so the height is 0, and we also know that the speed here was given 7.19 meter per second. Here at A, V is, well, it's given in centimeters per second. Let's change that. 0.657 meters per second. And the height here is something that we can solve for, given that we know all the other V's and H's. Now, what does this have to do with solving for the angle? Well, that'll come out later, but this is a conservation of energy question, and we're going to set it up like all of our other conservation of energy questions. Now, for this one, in addition to the system diagram, I'd like you to consider a free body diagram. The reason for this is because you've got extra forces going on here. This is your slope, and this is your skier. Your free body diagram is going to look like this. You're familiar with this, force of gravity, normal force, and then there's a force of kinetic friction going up the hill. Now, the normal force does no work because it's perpendicular to the direction of motion. The force of gravity does do some work in pulling the skier down the hill, but we don't have to consider that because we're going to put the Earth in the system, and so any work done by gravity will be taken care of by the EG bar in your energy bar diagram. But what is important here is that you've got this extra force doing work on the skier, negative work because it's in the opposite to the direction of motion, and that is going to be taken into account when we draw our energy bar diagrams. Okay, and that's what we're going to do next. So identify our system. We've got the skier and the Earth. Now, you have to, because of the friction now, consider that there is energy loss from this system, energy given off as heat or thermal energy, which we can identify here as Q, or you could use E with a subscript TH like your textbook does, and that is on account of the kinetic friction from our free body diagram. So our energy bars, we've got gravitational potential energy plus kinetic energy is equal to total mechanical energy. In our initial position at the top of the slope, we have a lot of gravitational potential energy. Say that much. We have a little bit of kinetic energy. It's going slowly compared to where it is at the bottom. And so the total energy will be the sum of those two. Then some of the mechanical energy is lost to thermal energy. So afterwards, our total mechanical energy is going to be lower than it was before. So I'm drawing that bar intentionally shorter. And down at the bottom of the hill, there's no gravitational potential energy. So that total energy is made up entirely of kinetic energy. Great. Now with a logical LOL diagram, we can go straight to our energy equation. Where our total energy at A is reduced by the thermal energy to determine the total mechanical energy at B. Now at A we have both EG and EK. The thermal energy is equal to the force of kinetic friction times delta D, and then at B we have only EK. And from here it's just a lot of substituting. The mass of the skier, 55 kilograms. Like I said, a lot of substituting. The force for the kinetic friction and the length of the incline were given. There it is. That's a lot of information organized in one equation, but it was possible because of your LOL diagram. Now this solves to give you the height of the top of the hill of 3.513 meters. Now, what good is that to us? We were asked in the beginning to determine the angle phi here for the slope of the incline. So now we know the length of the incline, we know the height, so it's just a trig ratio to figure out the angle. Close enough. All right, so to solve for phi, we know the opposite side and the hypotenuse. So sine of phi will be 3.513 meters divided by 11.7 meters. That solves to give you an angle. Phi is 17.5 degrees. Therefore, the angle of the slope is 17.5 degrees. To review then, once again, very important to start with a big clear system diagram where you can write down everything you need to know and what you're given. In this case, because there was an external force acting on our system, friction, we drew a free body diagram, then moved into the energy bar diagram that showed a thermal energy loss because of friction. That allowed us to set up the energy equation, solve for the height of the slope, and then use a trig ratio to find the angle. So that's how it works. Good luck with your own.